What's up, guys? Welcome back to another Algebra 2 lesson here with Mr. Gaines, continuing to look at solving exponential and logarithmic equations. In a previous lesson, we explored how to solve equations using the fundamental property of logarithms, the idea that logarithms and exponential functions are inverses of one another. And then we expanded on that, entering in the additional properties of logarithms and the change of base formula. Now we're going to kind of put all of those ideas and some potentially new ideas together in a method of solving a variety of exponential and logarithmic equations. So in problem number 6 here, we have a expression where we want to find the value of x, and in the directions it does say that we want to eliminate extraneous solutions. So we can use the fundamental property of logarithms here, but first we see that there are two different logarithmic expressions. So what we want to do is we want to go back to our properties of logarithms, where we know that if two logarithms are being added together, we can multiply their inputs combining the logarithms as long as the logarithms have the same base. And in this case, they do. They're both common logs. So what I can do is rewrite this function as log base 10, or the common log, of x times x plus 3. And that's still going to be equal to 1. Now, if I simplify that, that's going to give me the common log, or log base 10, of x squared plus 3x. And that equals 1. Now, I may want to simplify this expression, and in order to get into the x's where I need to solve, I need to use the inverse of a common log, which would be an exponential base 10 expression. So I'm going to take each side to the power of 10. Sorry, I wrote 1 down wrong. That should equal 1. And so in this case, it's going to equal 10 to the first power. Now, the exponential base 10 and the logarithmic expression base 10 will eliminate each other's operations, leaving you with x squared plus 3x equal to 10 to the first power, which is 10. Now, this gives us this quadratic equation that we can solve. We can solve this by subtracting 10 from both sides and then factoring the equation. Now, this isn't the only way to solve. It is a quadratic, so there's many ways to solve the quadratic, but this is a pretty straightforward factorization. So if we factor it into two binomials, first term in each binomial will be x, and we know that it has to be factors of negative 10, so a positive unit and a negative unit, and this would be a positive 5 and a negative 2. So if I were to multiply positive 5 times negative 2, that does give me negative 10. And if I were to do the distribution here, I would get a 5x, a negative 2x, which adds together to give me 3x. And of course, x times x is x squared. So now as I solve this, each of the factors individually could be set equal to 0. And then I would get x equals negative 5 and x equals positive 2. Now, one thing that we need to do is we need to check these for extraneous solutions. Now, there's a variety of different ways that we can do that. Remember, we've seen this before when we create a quadratic equation in the process of solving, and we did. We created a quadratic equation, x squared plus 3x, that was not there initially. When we create the quadratic equation, occasionally values will show up that are actually not solutions. So if I were to look at the graph of this, so I put in the left side of the equation, and I put in y equals 1, and I'm going to go ahead and graph. We're going to see that there's one intersection, and based on where this intersection lies, I can assume that this value is 2, and that negative 5 is extraneous. Now, some reasons that I can find out that negative 5 is extraneous is, let's go back to what we know all about, even before this graph here. Let's go back to what we know about logarithms. The input value of a logarithm must be positive. So if I were to substitute the log base 10 in this case of negative 5, if I were to do the substitution, try to put negative 5 back into this expression, log base 10 of negative 5 has a non-real answer, and so it's not going to be a solution. So remember that we can quickly eliminate negative 5 as a solution because it would give us a negative input value for the logarithms, which, based on what we know, cannot exist. We could also eliminate this as if we tried to substitute both values back into the equation. So if I tried to do the full substitution with -5, I would find that the equation would not be balanced or equal. Now I could try to substitute with 2 in this case. So log base 10 of 2 plus log base 10 of 2 plus 3, which is 5, and see that that answer would be 1. So 2 is a solution. So in instances where we create a quadratic equation, we do need to make sure that we check for extraneous solutions. If you're unsure of when to check for extraneous solutions, always substitute your answer back in for x and see if that's going to keep a balanced equation. If it is, that is the correct answer. If it's not, you either made a mistake or you have extraneous solutions. So another method for solving properties of logarithms is solving logarithmic equations is the uniqueness property of logarithm. So if I can get down to an equation with a single logarithm of base b equal to another single logarithm of base b, then their input values in this case r and s, must be equal. So as long as I have a logarithm on each side of the equation and the base is the same, then I can focus on setting their input values to be the same. We saw this with exponential equations. So we had if an exponential equation a to the x was equal to a to the y, then x had to equal y. We saw it's the same property that we had there, just now with logarithms. So this is helpful when you have logarithms on either side of equations, and they are all the same base. So in 7a, I have log base 10 of x plus 2, so I have one logarithm on the left side of the equation. I have two logarithms on the right side of the equation. I can only use this uniqueness property if I create a single log on the right side of this equation. Now remember, the product property allows us to combine these two logs of base 10. So this would be log base 10 of 7 times x, which is 7x. So because I have two logarithms, both of base 10, equal to one another, then their input values must be equal. And here I can subtract x from both sides to get 2 equals 6x, and then divide by 6 and get x equals 1/3, or 2 over 6. And again, I can check this by typing into my calculator, log base 10 of 1/3 plus 2, seeing this rounded answer, sorry, I need to insert a division here to make it 1/3. Seeing this rounded expression, and then inputting log base 7 plus log of 1/3, and seeing this rounded expression, and they are the same. So if you kind of get how that uniqueness property works, see if you can do problem B. Pause the video at this point and find an answer for B. Hopefully you were able to find the solution for B. In B, we see the natural log. All of these are a natural logarithm, so they all have a common base. So if I can get a natural log on each side of the equation, then I can use the uniqueness property to solve. So in B, I can combine my logarithms on the left using the quotient property. So the natural log of 87 minus the natural log of x is the same or equal to the natural log of 87 over x. I can divide the input values. In this case, now I have a natural log on each side that is equal to one another, so their input values must be equal. So 87 over x equals 29. To get x out of the denominator when solving here, I do need to multiply both sides by x. And then now I have 87 equal to 29x. And I can divide both sides by 29. So 87 over 29. And this would be the exact answer. We can reduce that fraction actually in this case and get that x equals 3. Again, you could check this by typing in natural log of 87 minus the natural log of 3, and seeing that that value would be approximately 3.367. And also typing in the other side of the equation, evaluating it in the calculator, seeing that value is approximately the same. Thus, our answer here is correct. So the uniqueness property of logarithms works when you can balance an equation, or not balance the equation, but you can get a logarithm on each side of an equation that has the same base. Now let's look at some different scenarios where we have to solve for a variable, and we have to incorporate a variety of different methods that we have chosen. So if I take a look at problem 8, we want to make sure that we eliminate extraneous solutions in our process. So in 8a, I notice that I'm dealing with natural log here. So I see that I have two natural logarithms, but I have a third term that is not a natural logarithm. So I'm not going to be able to use the uniqueness property because I'm going to have a term here that does not meet the criteria of being just one single logarithm. However, I can use the fundamental property of logarithms. I can only use that if I have a single logarithm, 1 in my entire equation, based on what we know. So what I want to do is use some of my logarithmic properties on the left side of this equation. I may recall that the power property for logarithms allows me to rewrite 2 times the natural log of 5 as the natural log of 5 squared, rearranging that coefficient as an exponent. Now this would give me the natural log of x plus 5 minus the natural log of 25. And now this isn't the only way that I can complete this problem, but now I may notice the quotient property. The quotient property allows me to combine these two logarithms by dividing their inputs. And now I'm at a place where I have created a single logarithm on the left side of the equation. If I can get rid of this logarithm, then I can work through the process of solving. So here, what I can do is use an exponential equation with the same base that my logarithm has, or base e, Euler's number. So I'm going to create an exponential expression on both sides of the equation with base e. On the left side, the base e and the logarithm with base e will eliminate each other, leaving us with x plus 7 over 25 equal to e to the 0.9 power, Euler's number to the 0.9 power. Now I still need to do a few steps here to get x by itself, so I'm going to need to multiply both sides by 25 to eliminate that fraction. So I'm going to get 25e to the 0.9 power. And then I would need to subtract 7. So x is going to be equal to 25 times Euler's number to the 0.9 power minus 7. This would be the exact answer for my equation. If I want to find a rounded answer for this equation, I can go ahead and evaluate this expression in my calculator and see that this is going to be approximately, let's round that to 2 decimals, 54.49. Now again, I may want to check this answer in my calculator. So I'm going to take the natural log of x, which is this answer, plus 7 minus 2 times the natural log of 5. And when I evaluate that expression, it is going to be equal to 0.9. So we have done this correctly. So here we used some properties of logarithms to rewrite expressions, and then we were able to apply the fundamental property in inverse operations to be able to get x down into a ratio or even a linear function here that we could solve. Let's take a look at B. In B, I'm going to go ahead and use a slightly different method, but the initial part of this method is going to start the same. I see here that I have 2 logarithmic expressions on the left side of the equation, so I can try to combine those using the quotient property. So this would give me log base 10 of x plus 12 over x, dividing their input values. Now I notice that the other side of the equation is also log base 10. Thus, I can use the uniqueness property. So the uniqueness property would tell me that the inputs of these logarithms would be equivalent. So now I just have x plus 12 over x equal to x plus 9. In this case, if I want to get rid of my fraction, probably the easiest way to do so would be to multiply both sides by x. So if I multiply the left side of the equation by x, I'm going to get an x squared plus 9x. Now I'm going to go ahead and combine or get all of my terms to one side, as this is a quadratic equation. So I'm going to subtract x from both sides and subtract 12 from both sides. And if we look at this expression, we may notice that this could be a problem that we factor. Not the only way to solve a quadratic, but this is a quick factorization. I would have x and x that multiplies to give me x squared. I would need numbers that multiply together to give me a negative 12, and through distribution add to give me negative 8x. So those numbers, oh, sorry, I made a mistake here. This should be a positive 8x. There we go, positive 8x. Sorry, can't get this off my screen. So actually, this problem is not going to be an easy factorization. I'm not going to factor this problem. Instead, you could use the quadratic formula. I'm going to go ahead and use the method of completing the square. So I'm going to go back a step. Apologize for this. I'm going to go back a step and leave this as 12 equals x squared plus 8x. Now remember, to complete the square, I need to add a c value that is 1/2 of b squared. So I'm going to add 16 to both sides. I'm going to add 16 to both sides. This would give me 28 equal to x squared plus 8x plus 16, which we know, or should know, that x squared plus 6x plus 16 can be factored into x plus 4 and x plus 4, or x plus 4 squared. In this case, I can square root both sides. So if I square root both sides, I'm going to get the square root plus or minus the square root of 28, which I will simplify in a little bit, equal to x plus 4. If I subtract 4 from both sides, I'm going to get negative 4 plus or minus the square root of 28, which 28 breaks down to, if you need to, we could write this over here. 28 breaks down into 4 times 7. So the square root of 4 is 2, root 7. So this is the value for x. X is equal to negative 4 plus or minus 2 roots of 7. I'm going to go ahead and write this as two different expressions. And the reason that I'm going to write this as two different expressions is because we do need to make sure that we check for extraneous solutions. So this is maybe a difficult expression to recognize, but let me go ahead and type in negative 4 plus 2 roots of 7. Now, negative 4 plus 2 roots of 7 would be a positive number, and we may not be exactly sure if this is a correct answer. We could substitute that in and find out that negative 4 plus 2 roots of 7 would be a correct answer. Now, if I took a look at negative 4 minus 2 roots of 7, what I'd see here is that this is a negative number. And what's especially important about this being a negative number is that would give me a negative value inside of this logarithm. So x can actually not equal negative 4 minus 2 roots of 7. If you substituted that back in, you would find out that this is not going to be a solution. It's not going to give you a real answer. So here we have our real answer. I'll move it down a little bit. Move that down to the bottom of the problem here. The real answer is negative 4 plus 2 roots of 7, which we can list as an approximate value of 1.29 if we wanted or needed that approximate value. So here we see a couple of different methods for solving logarithmic equations. Let's look at one more example type of problem, and that's finding the value of the variable in exponential equations. So we've already done some of these problems using the fundamental property of logarithms, and here we're going to continue to use that. Now remember, in order to use the fundamental property of logarithms, I need to isolate the exponential equation. So if we think about solving these in a linear pattern or reverse order of operations pattern, we do subtraction and addition first, followed by division or multiplication, then an exponent, and then work within parentheses. So what I see in problem number 9 is that in order to eliminate the exponent, I need to first move the 1. So I'm going to add 1 to both sides here. And if I add 1 to both sides, I get 4 to the 3x power equal to 9. Now, in order to eliminate the exponential expression with base 4, I need to use a logarithm of the same base. So log base 4 of 4 to the 3x power. I'm going to take that of both sides of my equation. And on the left side of the equation, the log base 4 and exponential base 4 expressions are going to eliminate each other as they are inverse operations, leaving me with just 3x. Now I can divide both sides by 3, so x is equal to exactly log base 4 of 9 over 3. Now this is the exact answer. How do we get a rounded answer for this? Well, remember the change of base formula. If I want to evaluate this in my calculator, I can. What I need to do is I need to evaluate the numerator as a log, maybe the common log of 9, divided by the common log of 4. So the numerator would round to this approximate decimal, which I could then divide by 3. So the approximate answer here would be 0.53 if we rounded to 2 decimals. Now again, I could check this by going back to the original expression and inputting that answer that I got for x and seeing that this is slightly rounded, which slightly rounds my answer, but it gets us really close. So we can assume that if this was non-rounded answer, that I would have the answer exactly equal to 8. So here I'm using the logarithmic or the fundamental property of logarithms, and we also use the change of base formula that we learned in notes video part 3. Now let's take a look at B. B is a little bit more complicated because I have exponential functions that are no longer the same base. So how do I deal with this kind of expression? Well, what I can do is try to eliminate one of the bases. So let's go ahead and let's use log base 5 to eliminate the exponential expression on the left side of the equation. So I'm going to take the log base 5 of both sides of the equation. Now on the left side of the equation, it eliminates the logarithmic base and the exponential base, leaving me with just x plus 1, which is good. However, on the right side of the equation, I've created a little bit of a mess here. I no longer have, or I now don't just have only an exponential expression, I have an exponential expression inside of a logarithmic expression with a variable in the exponent. So a lot of work to get that variable out, or seemingly a lot of work to get that variable out. If we think about our logarithmic properties, I can take any value in the exponent and rewrite it as a coefficient for the logarithm. So what I'm going to do here is I'm going to leave the left side of the equation as just x plus 1 for right now. I'm going to rewrite this as a coefficient x. Then what would be left inside of the parentheses is 6 to the second power. So I'm using the product property for logarithms to pull out that x. And 6 to the second power we know is 36. So I could just rewrite this as x times log base 5 of 36. Again, using the the power property. Now I notice that I have logarithms on two values of x on opposite sides of the equation. I'm going to get them together. I'm going to subtract x from both sides, subtract x times log base 5 of 36 from both sides. I'm also going to subtract 1 to move that to the other side of the equation. So here on the left side of the equation, or what I've done is just rearranges the x's on the same side. Now on the left side of the equation, I see two x's. This x is attached to the logarithm through multiplication. This x is just by itself, but these two terms have a GCF of x. I can factor out an x, which leaves me with 1 minus log base 5 of 36. So if I factor out an x, now I have a single x multiplied by an expression that I can divide from both sides. So in this case, x is equal to negative 1 over 1 minus log base 5 of 36. That value can be typed into the calculator to be approximated, negative 1 divided by 1 minus, remember I need to use the change of base formula here for log base 5 of 36. And in using the change of base formula, we can get the approximation of 0.82. Let's try that again. So we see that same situation here in C. So in C, I'm going to go ahead and use the log base 4 of both sides, or take the log base 4 of both sides, to eliminate at least one of my exponential expressions. In doing so, I create 2x minus 1 on the right side of the equation. I'm also going to use the power rule for logarithms to get x out of the exponent and now as a coefficient of log base 4 of 7. Here I can get my x's to the same side, so I'm going to subtract 2x from both sides. So now I have x times log base 4 of 7 minus 2x equal to negative 1. Then I can again use the GCF of x, factor out the GCF of x, and then divide by that expression to finally get x by itself. So x is equal to log or negative 1 over log base 4 of 7 minus 2. And so if I type that into my calculator, I have negative 1 divided by, using the change of base formula, log of 7 divided by log of 4, and that's subtracted by 2, which would give me an approximate value of 1.68. So here we see some creative uses of not just the fundamental properties of logarithms, but also the power property of logarithms to get x into a position where we can solve. And this looks like a good place to stop. So here we see a variety of examples of how we can solve exponential and logarithmic equations. As always, thank you guys for tuning in, and I'll see you soon.